So, thanks. Let's start with principles of Cilium and eBPF. And then we talk a bit about networking. I'll talk about cluster mesh, security, observability, service mesh, and finally Tetragon. I'll try to not spend too much time. I'm aiming for roughly half an hour of presentation, and then we switch to hands-on so you have enough time to actually test on your own. So who are we? I'm Raphaël Pinson. I'm a technical marketing engineer at Isovalent, now Isovalent at Cisco, since we were acquired a little bit over a month ago now, right? 2 months ago. And with me is Dean Lewis, also joining from the UK, also a technical marketing engineer in the same team. I'm also a CNCF ambassador, and I try to go to several conferences and talk about Kubernetes, cloud-native technology, and specifically networking and security in this context. So we're talking here about several things. We work for Isovalent, now Isovalent at Cisco, and Cilium and eBPF are actually open source technology. So Cilium was open sourced and then given to the CNCF, to the Cloud Native Computing Foundation that manages projects such as Kubernetes, Prometheus, and many more, over 20, maybe even 30 projects now. So Cilium is an open source project that is managed within the CNCF. And a lot of the contributors are still from Isovalent. And Cilium is strongly based on eBPF, which is the technology of the kernel, of the Linux kernel originally, now expanding to other kernels, because Microsoft, for example, is interested in porting it to Windows and has started the work on porting it to Windows. And eBPF was co-created by two people who now work. One is at Meta and one is currently working at Isovalent as well, and one of the founders of Isovalent. So this technology, eBPF in the kernel, is what makes Cilium and Tetragon as well, a sister project of Cilium, able to be extremely powerful, extremely scalable, and allow for very fine-grained control of the OS and a very fine-grained control of observability, security, and networking in the context of cloud native specifically. So I like to say that you've probably used eBPF if you have, for example, an Android phone. If you look at which applications are using the bandwidth on your phone, this is using eBPF because that's not a native functionality of the kernel. So we need to extend the functionality of the kernel. And extending the functionality of the kernel can be done in many ways. You could use kernel modules. You could patch the kernel yourself. The best way currently is to use eBPF, as it allows to expand the functionality in the form of, I would say, callbacks, right? A little bit like what JavaScript does in your web browser, where you can attach to events in the kernel, events in the OS that we call hooks in the context of the kernel. And these hooks can be used to trigger programs that have been injected in the kernel using the eBPF subsystem. So typically, if you have, let's say, process, let's say it's a shell, for example, you have a shell like bash, and you're executing a command, let's say ls, this is going to trigger an exec via syscall in the kernel. And this exec via syscall will result in the new program being scheduled for execution in the kernel. Well, with eBPF, what you can do is that you can actually hook on the syscall and execute a program that you've decided you want to execute every time an exec via syscall is triggered, or the event is triggered. So you could have like a little program like this one, for example, which will observe what's happening. Every time the exec via syscall is called, it will retrieve the PID of the calling process and store it in a data structure that we call an eBPF map, where it can be read by another eBPF program or even by a program in user space, which can allow for very low overhead observability in the kernel. So the E in eBPF stands for extended. Originally, BPF was a subsystem essentially for networking, and the E for extended stands for the fact that eBPF allows to control and to hook into much more than just kernel events in a kernel. It can be based on reading and writing files. It can be based on networking. It can be based on security-related events, lots of different things. So typically, you could attach a program to any process that reads a file descriptor, that writes to disk from a block device, It could be attached to network events, such as connecting to a socket in the kernel. It can be used to extend, enrich the logic in the TCP/IP stack, and so on and so forth. You can attach to kernel functions. You can attach to user space functions using new probes, system calls, trace points, and so on. In the context of Cilium, obviously, we're going to attach very often to events that have to do with networking. Typically attaching to network devices. This could be physical network devices. It could be virtual network devices. It could even be virtual network devices specific to a pod, for example. So we can attach to network devices on every pod and hook whenever there's traffic that arrives or leaves the pod through this network device. We can actually act on this traffic to steer the traffic in a specific way, either to block it or to decide where to send it. So this can typically replace logic based on IP tables and traditional routing. There is actually a documentary on eBPF. If you want to learn more, I would recommend you look into this. You can just look for eBPF or unlocking the kernel on YouTube. It's free. You can see it there. I think I found it really interesting to actually understand the scope and the potential of eBPF. So with this, what is Cilium? Cilium is first and foremost a CNI plugin. So in Kubernetes, there is no standard implementation for networking. What there is instead is a standard specification that is called CNI, for Container Network Interface. And pretty much every Kubernetes distribution provides a default CNI plugin, right? Some distributions use a standard CNI plugin. That could be Calico, that could be Flannel, that could be Cilium, and so on. Some distributions actually make their own CNI plugin. This is the case of AWS EKS, for example, that uses the VPC CNI plugin by default, which they make specifically for AWS. So Cilium is a generic CNI plugin that can be used on many different Kubernetes distributions. In fact, pretty much any Kubernetes distribution. And it provides the basic of networking connectivity between the pods, between the nodes, as well as a possibility to replace kubeproxy for the implementation of Kubernetes services. So it can replace the default load balancer, which is based on IP tables in Kubernetes. And then it has advanced functionalities out of the box, such as multi-cluster, VM gateway, the possibility of having VMs access the network of the pods and vice versa, with metadata for services, security, such as the implementation of network policy, encryption with IPsec or WireGuard, and it's strongly based on identity. This is what matters the most, I would say, especially in the context of cloud native. In cloud native, we care very much about metadata. It's all about turning pets into cattle, right? This is the extension of the whole logic of turning pets into cattle. And you care about this if you're into platform engineering. It needs to scale. And something that doesn't scale is assigning IP addresses and names to every devices. That doesn't scale well. So one of the ideas of Kubernetes and of container orchestration in general is that as you scale, you want all your entities, all your elements, all your pods to be treated as cattle. So you identify them by labels, and you can have 1,000 pods with the same labels, and they're treated the same way because they share the same label set. And this is the idea in Cilium, is that we're going to treat pods, we're going to treat entities based on their labels at the core. And at the core, that means for us in the kernel itself. So because, and thanks to eBPF, the kernel itself is aware of Kubernetes metadata and is able to make routing and security decisions based on the metadata, based on the scalable identity and not the specific identity, such as IP addresses or the name of a specific pod, right? Besides this, Cilium provides observability, and because we do all the routing and security in the kernel, we also have observability in the kernel thanks to eBPF. So Cilium can provide metrics in the form of Prometheus metrics, can provide flow visibility. There is actually a service map, so service dependency with a UI that you'll be able to see as well. So let's look a little bit at the functionality that you can have. The base brick is the CNI plugin, the implementation of Kubernetes networking itself. I'm saying Kubernetes, it's not necessarily Kubernetes actually, because CNI is also implemented in other solutions such as HashiCorp Nomad, for example, and there's people that use Cilium in Nomad because it's CNI compatible. So Cilium can be used in the context of CNI compatible orchestrators or systems. So in the context of CNI, Cilium provides IPv4 or IPv6 networking. It could be based on a cloud SDN. It can adapt to Google Cloud, Amazon, Azure, and so on and so forth. There's quite a few cloud providers that have actually adopted Cilium as the default provider for the Kubernetes solutions. On-premise, it can do BGP as well as overlay. There's implementation for SRv6, egress gateway. I'll get a bit more in details on egress gateway later. It can even do NAT IPv4 to IPv6 and vice versa. Multi-cluster, the possibility of meshing multiple Kubernetes clusters to have a unified data plane while keeping separated brains, I would say, separated API servers. Security with network policies from layer 3, layer 4, which is the basis, all the way to layer 7 and DNS support. Encryption with IPsec and WireGuard. Load balancing with the possibility of replacing QProxy with Cilium itself and different algorithms for load balancing using, for example, maglev or DSR to keep the calling IP, the source IP, outside of the cluster, from outside the cluster. So DSR is direct server return. Observability with the possibility of having metrics, so Prometheus metrics. We can produce OpenTelemetry traces with Hubble as well. Service maps, logs, and all of this can obviously be exported to the platform of your choice. It could be Prometheus, it could be the SIEM of your choice, it could be Elasticsearch, Splunk, Datadog, you name it. And service mesh. Cilium provides an Envoy proxy on every node. And Envoy, as you might know, is the basis for most service mesh implementations, such as Istio, for example. And so Cilium allows to do routing and security all the way to layer 7 using the Envoy brick that is provided on every node to implement an ingress controller, as well as gateway API and all kinds of advanced routing and security. And on top of this, there's Tetragon. Tetragon is a sub-project of the Cilium project, which provides runtime security. It uses eBPF to observe pretty much anything that can happen on your node and provides observability. You can have traces, you can have metrics, and it provides enforcement as well. It can allow you to kill processes when you don't like what's happening real time, or even modify the behavior of the kernel when you don't like what's happening. Let's say someone is trying to read etc shadow, you can provide a fake answer, fake content as a reply. There's many people that use Cilium. If you're interested, this is not to brag about Cilium, but if you look at Cilium.io, what's interesting is to look at the use cases. A lot of people use Cilium for very different things. There's blog posts, there's videos that have been posted there that give you a great idea of what can be achieved with Cilium. Cilium has graduated last year. This is old news now. I should probably remove that slide. But this means that Cilium is now a graduated project within the CNCF, and it's actually the only CNI plugin that is an official CNCF project and is graduated. So it's now the de facto CNI standard in Kubernetes. So let's dive a bit into networking. Need to keep an eye a little bit on the time, make sure not taking too long. So like I said, in Kubernetes, there's no standard for networking. You need a CNI plugin to implement networking. And there is a component that's provided by default, which is QProxy, to provide layer 3, layer 4 load balancing in front of the pod. Cilium can replace both with eBPF. So it can provide cross-node, cross-pod communication, as well as load balancing for the virtual services in Kubernetes. So this is the logic of services in Kubernetes, where you have a virtual IP in front of multiple pods to provide layer 3, layer 4 load balancing. Traditionally, this is implemented using IP tables or some form of net filter logic, because it could be IPVS as well. And this uses a linear logic, kind of a sieve, where you go over all the rules until you find the right one. And this doesn't scale very well. If you have a cluster that has hundreds of nodes, thousands of services, you'll soon start seeing problems in scaling. It could be that your pods will start taking seconds and then minutes to start because you need to add so many IP table rules all over the place in order to start a new pod. Even the load balancing itself might suffer from this performance issue because IP tables is great, but it just wasn't made for this kind of scale. On the other hand, if you have an algorithm that is based on eBPF for this kind of load balancing, then you can have a per CPU hash table, which scales pretty much constantly, right? So adding new pods to a rule that already exists pretty much has no impact on the performance of the routing algorithm. One thing that happens very often when adopting Kubernetes technology and porting applications to Kubernetes is that, let's say you have an application that used to access a database. It's called legacy database here. It doesn't have to be legacy. You don't need to have your database in Kubernetes, to be honest. But you had an application that used to be sitting there, and you could filter the access to this database based on the source IP. And now that your application is inside Kubernetes, well, when the application reaches out to the DB, you cannot really identify it anymore because the source IP will be either the source IP of one of the nodes if you're using an encapsulated mode, and then the node will source NAT the traffic, or it might be the IP of the pod if you use direct routing, but even then you won't be able to identify which application it is. So there is a feature that is called egress gateway, and this feature allows you to specify that when this application here, this pod, wants to reach out to this external IP address or CIDR, it needs to exit the cluster through a specific node and a specific address. So here we're saying it needs to exit the cluster through 1024.05, which is an IP that is located on this node. And then whenever that pod reaches out to the outside, or these pods reach out to the outside, the source IP address that will be seen from the database will be this IP address. So you'll be able to filter using firewall, using the database itself. So that gives you the possibility to actually filter source traffic coming out of Kubernetes in an efficient way. You can see examples of this hands-on a bit later. Platform integration is super important. The fact of being able to adapt the networking configuration to the environment. And this is, if you've worked quite a bit with content orchestration and Kubernetes, you know that what matters the most, really, what makes Kubernetes extremely performant is how well you can integrate and tune the whole system to take advantage of the underlying infrastructure. So in the case of Cilium, Cilium has an operator. This is not really a Kubernetes operator, so to say. It's a component that runs in the cluster and takes care of anything that is cluster-wide logic. In particular, it can be linked to linking with the cloud provider. For example, for IPAM. So in the case of IPAM, every node will be responsible for starting new pods using the kubelet and assigning IP addresses to the pods. So we'll have CRDs that will list the IPs that are available to distribute to the pods. And typically, if you consider, for example, AWS EKS, so the default Kubernetes service from AWS, it uses direct routing with IPs that are assigned to each pod from the VPC routing IP CIDR, right? So in this case, the Cilium operator will talk to the EC2 API, to the Amazon API, and retrieve the VPC IP addresses that are available. It will reserve IP addresses and assign them to the nodes, and then tell the AWS API on which nodes these IP addresses have been assigned for routing purposes. So this is the type of integration that Cilium knows out of the box, and allows to tune to the way Kubernetes clusters are made to function in different environments. Let's talk quickly about cluster mesh. Cluster mesh is the possibility of meshing multiple clusters into one data plane. I'll start with what it is not. It is not federation. It is not multiple clusters federated with the Kubernetes API service talking to each other in a federation. What it is that every node on all the clusters that are federated have a Cilium agent, and these Cilium agents are able to exchange information, to exchange metadata. This is unbeknownst to the clusters themselves. The Kubernetes clusters that participate in the mesh are not aware of being in a mesh. So what this allows to do is sharing information to provide typically cross-cluster services with cross-cluster load balancing. It can provide an identity-aware security and network policy system where you're able to write network policies that say service A in cluster 1 is allowed to talk to service B in cluster 2 using metadata, using Kubernetes metadata and not IP addresses. It can provide observability where you can see traffic flowing between pods, between identities in different clusters. Encryption as well. You can typically have WireGuard encrypted traffic between pods in different clusters. The routing can be extended between different clusters, and you can go all the way to service mesh logic with ingress, gateway API, and so on. So the way this works is that you'll have multiple clusters that are meshed. At the moment, the limit is 511 clusters that can be meshed together. I don't think this has been done actually, but I've seen a blog post recently of someone that is trying to achieve it, to have 511 clusters meshed. And what you have is that you can have virtual services, so Kubernetes services that load balance between multiple clusters. So it's the same service in different clusters, in the same namespace on different clusters, and the traffic will be load balanced between the clusters. So that if there are backends, pods that die on one side, let's say on cluster 2, the traffic can be redirected to cluster 1. It's possible to implement shared services with this logic. For example, here I have 3 clusters that are meshed with a virtual Vault service here, because there's no pods for the Vault service in cluster 1 and 2. It all redirects to cluster 3. So you could say, well, you can do this without cluster mesh. This is true. You could do this without cluster mesh, but you would need to have some kind of public load balancer here, and you would need to manage authentication and authorization yourself. Whereas here, the traffic is pretty much managed as in terms of routing and security, the same as if it was one cluster. Cilium considers it as one data plane, which means that security, authorization, authentication and authorization can be managed from the standpoint of Kubernetes metadata using labels and network policies. You can even split services. You can go further than that. Let's say you have like 2 clusters with stateless applications. Let's say it's your front end. It can scale as much as you want. You have 1 cluster in AWS, 1 cluster at Google's, and there's a service that you cannot scale very easily. So you'll put in a centralized cluster, and then using this logic of virtual services that are shared between the different clusters, you can actually redirect the traffic so that the pods in both of these stateless clusters think they're accessing a local service, but the traffic is actually transparently redirected to a third cluster. You can use affinity, so you can say, if possible, use local pods to implement the service and only go to a remote cluster if there's no local pods available. Or you can use remote service affinity to access remote pods by default and only go to local pods if there's no remote pods. This is not as useful. It's maybe a little bit more rare, but there can be reasons for this. Pricing, for example, if there's a service that is more expensive locally than it is in another region, or it could be that you want to implement some kind of cross-region backup or something like this. The way we're doing this is using basic resources in Kubernetes. So in this case, we use a service, and we're simply putting annotations on it. The annotation actually here needs to be updated. Now it's service.cilium.io/global, but the logic is still the same. You can set up a service as global and set the affinity to be local or remote. Same for remote. You could go all the way to doing canary rollouts using multiple clusters with a layer 7 routing using ingress or gateway API in the front, with waiting to go either to one service or another in a second cluster. You could have network policies here, and then use a shared service with cluster mesh to access the database. So the sky is the limit here. Let's talk a bit about security. I've mentioned network.
Raphael, we just have one question that came through on Slack. Can I use cluster mesh with SRv6 and also can I use it with BGP?
This is a good question. With BGP, that should be possible. It won't use BGP itself, but you, as far as I know, you can join clusters that use direct routing and could use BGP. As far as SRv6, I'm not sure. Do you know about this, Dean?
No, but I'll have a quick look in the background for that as well.
Yep. Thanks. So I've talked a bit about security already, about network policies. Cilium cares a lot about identity-based security. Like I said, identity in Cilium is strongly based on labels, on Kubernetes metadata, or metadata in general, because Cilium can actually run outside of Kubernetes. As much as possible, Cilium will try to keep the identity with the traffic, with the packets. Based on this, Cilium will implement security using network policies. You can use standard network policies, Kubernetes network policies, as well as specific Cilium network policies. Why do we have a specific CRD for Cilium? Because there's functionalities that just cannot be expressed using standard network policies. And we're actually pushing to get these functionalities into the standard resource type. So what is standard is layer 3 and layer 4. Layer 3 and layer 4, layer 3 says, this pod here called frontend is allowed to talk to the backend. Whatever they want to say is not my problem. They're allowed to communicate. This is layer 3 authorization. Layer 4 is a little bit more specific. We're going to specify which protocol is allowed. They're allowed to talk on port 80 protocol TCP. Layer 7 is not supported by standard network policies in Kubernetes, so you need to use Cilium network policies for this, and it will say, yes, frontend is allowed to talk to the backend on port 80 protocol TCP, but only if this is HTTP traffic and if it's using the GET method on the /public path. You can filter by header, you can filter by a lot of different things, but this means that Cilium is actually parsing your layer 7 traffic. And in this case, Cilium will rely on the Envoy process, on the Envoy pods, on the Envoy workers that are deployed on every node in order to do the layer 7 parsing and decide if the traffic is allowed or not. So layer 3, layer 4 is implemented in pure eBPF. Layer 7 requires Envoy. But it's automatic, it's transparent. The way this looks, this is an example with Cassandra. Most people will actually use HTTP, but just to show that this is not limited to HTTP. Here we have a network policy that applies to the Cassandra application. And it allows ingress to port 9042 protocol TCP. So this is a layer 4 rule. And here we're adding a layer 7 rule, which says only allow it if the protocol is Cassandra and if it's a select on my table. So this is layer 3, this is layer 4. This layer 4 rule will be interpreted and applied in the kernel by an eBPF program. And if this passes, the traffic will be redirected to Envoy, and Envoy, there'll be an Envoy listener that is programmed to apply this rule here and deny the traffic with a 403 if it doesn't match that condition. In addition to this, one common problem with network policies and standard network policies is DNS. Is what if you want to allow traffic to or from IP addresses or entities that are outside of the cluster and don't have the metadata to classify them. Well, in Cilium, we have DNS-aware network policies from layer 4. And what this does is that you can actually have a rule that will force traffic from the pods to kubedns being the internal DNS resolver in Kubernetes, to be proxied through Cilium. And then Cilium will build a cache of the DNS requests that have been made by which pod to which DNS name and what were the replies. And based on this, when this pod makes a request to this IP, Cilium will know that this IP was a reply to this request, and it will allow it based on the domain name that is allowed. So you can secure traffic to the outside of the cluster based on domain names. This can also be done in the other way. It's just a little bit more complicated, but it is also possible for ingress, in case you're interested. So all in all, these are all the layer 3 matching capabilities. The most useful, the most used are based on pod labels, namespace name and labels, service account possibly. You can say this service account is allowed to talk to this service account. Service names, cluster names in the case of multi-cluster, so cluster mesh. DNS names, including regular expressions, like I just showed. CIDRs, potentially with exceptions. So this whole CIDR minus the subnet. It could be based on cloud providers' metadata as well, or logical entities. So Cilium has out-of-the-box logical entities for everything inside the cluster. That's called cluster. Everything outside the cluster, that's called world. The local host or other hosts, or the Kube API server, for example. If you have a pod that needs to access the Kubernetes API server, you can say it's allow traffic to entity Kube API server. So you don't need to know the IP address. Once we do the routing and security, we can observe what's happening, and we can show you a lot of things. And this is what Hubble is about. So Hubble is the observability component of the Cilium stack. Hubble has a CLI, it has a web UI, and it can export metrics in the form of Prometheus metrics to the platform of your choice. So this is what the CLI looks like. Here I have an example where I have a default namespace with 4 pods, and you'll see that we have a lot of examples and a lot of labs based on Star Wars stories to make it a little bit more entertaining. So here we have 4 pods. There is a TIE Fighter pod, an X-Wing pod, and 2 Death Stars, because sometimes it happens that one Death Star explodes, so it's good to have a second one. And here we can see with Hubble what is happening. So the lines here, the comments are obviously added for clarity. They don't show in the output yet. Maybe in the future, you know, who knows, with AI, we could do something like that. So here we have the X-Wing pod in the default namespace reaching out to the DNS provider, kubeDNS, implemented by core DNS in this case, and kubesystem. We can tell that this is traffic going out to port 53, protocol UDP, standard DNS, and it goes through proxy, which means Cilium is caching the DNS response like I described earlier. We see the response here. And so we know that the X-Wing has done a DNS request. Actually, the DNS request it was making was for Disney.com, www.disney.com, because it was about to make an HTTP request to Disney.com. And so now we see the traffic from the X-Wing to Disney.com on port 443, and Disney.com is identity world. Here we can see the ID numbers for internal identities allowing to debug traffic. It goes to stack, which means it's going to the network stack, to the underlay, and exiting the cluster. And then we have the answer going from Disney to endpoint, meaning to the pod. And we have the SYNAC and ACFIN and then RST. So we see the entire TCP communication here. We can check that everything went fine. Finally, here's an example of the X-Wing trying to talk to the Death Star service in this namespace, and we see that it was denied by a policy. So this is the kind of information you can see with Hubble. You can see the traffic, you can see details of the traffic, and you can also see when traffic was denied. In this case, it was denied at layer 3, layer 4. You can filter here. You see here that I filtered using metadata, using a label of the pod. So this pod has a label class with value X-Wing, but you could filter by namespace, you could filter by name, and so on, by service, and so on. With the same information coming from Hubble, we also have a UI, and this UI provides a service map. So using, by default, the last 5 minutes of buffer from Hubble, we can build the communication between the different Based on the communication between the different components, we can build a service map and show exactly which components talk to whom. And you can even see that there's some layer 7 information here because we've enabled layer 7 information. It goes through Envoy, and Envoy actually gets that information. So which method was used, which path was requested, what was the return code, the response code from the service. So you can have details. And here at the bottom, you have all the flows. And if you click a flow, you'll get the details of that flow. You can integrate with Grafana. So both Cilium and Hubble and Tetragon as well produce Prometheus metrics as well as potentially OpenTelemetry traces. And all of this plus the logs, JSON logs can be sent to, for example, Grafana. But again, it could be Elasticsearch, it could be Datadog, it could be Splunk, whatever platform. We do have Grafana dashboards that are ready to be used, and you'll see some of them in the labs. Finally, we can use, well, not finally, there's still Tetragon, sorry. We can use Envoy for service mesh, so layer 7 routing, logic, and security as well, layer 7 security. If you want to implement service mesh using Cilium, you could use Cilium as the layer 3, layer 4 base and then deploy a service mesh on top, such as Istio, for example. That works. Most people don't need the complexity of Istio for their service mesh implementation. Essentially, most people, they want layer 7 observability, they want layer 7 security, and they want maybe encryption, cluster mesh, and that's pretty much it. And routing logic using ingress or gateway API. So Cilium has all of this out of the box. So for most people, there will be no need to deploy an extra service mesh solution. And Cilium will be enough for their need. So what has been added, and this is not extremely new, actually. I should have made this slide because this has been a while already. So Cilium now has an out-of-the-box ingress controller. It has a gateway API implementation, which actually supports gateway API v1, so the stable version of gateway API. It has support for SPIFFE for mutual authentication since 2 releases. And it has an Envoy CRD. So there is a CRD in Cilium that allows you to program the Envoy worker that is provided with Cilium if you want to do anything that is advanced. If you're interested in this, there's labs for each of these. We have a lab for ingress controller. There's 2 labs for gateway API. There is 1 lab on mutual authentication, and there is even a lab on advanced Envoy use cases and programming. So the idea, the way we see things is that we're going towards the simplification of service mesh. Say a few years ago, if you wanted to do service mesh, you needed to use a specific library for your application. Now we're at the stage where most people will use service mesh with a sidecar. We think service mesh should be entirely transparent. It should be at the kernel level. We're not going to provide changes to the kernel itself because that would take a long time to get into your distributions and it would be quite complex. But using eBPF and occasionally sending traffic to Envoy if we need to at this point allows to have a transparent layer of service mesh that is provided out of the box and as close as possible to the kernel, providing efficiency and scalability. We also have, instead of 1 sidecar per deployment and per pod, we have one Envoy worker per node, which means that it's more efficient and it consumes less resources, in particular RAM. And it makes the pod start faster because Envoy is always ready to accept traffic. So you don't need to start Envoy in every pod in order to be able to use it. So the approach at the moment is everything that can be done in the kernel will be done in the kernel using eBPF. That's layer 3, layer 4 routing and security, canary, multi-cluster, network policy at layer 3, layer 4, mutual authentication. Everything we can do in the kernel should be transparent and in the kernel. Things that are currently not possible because of the limitations of eBPF, such as layer 7, load balancing and ingress, retries, TLS termination, that's at the moment not possible. This is sent to the Envoy proxy at the moment. Again, totally transparent, just so you know it goes through the proxy. In the future, it is totally possible that these will actually be ported to eBPF once there is a way in eBPF to do these things. I'll pass on this. I don't want to spend too much time because I want you to be able to put your hands in and actually play with the tool. So last part then, Cilium Tetragon. This is runtime security. It allows to observe anything that happens on your node using eBPF and potentially react to the events happening on the node and block potential harmful actions. So with the Tetragon agent will generate eBPF programs in the kernel of every node, and it can watch process execution, syscall activity, file access, network, namespace escapes in the case of Linux namespaces, network, and so on and so forth. So it can provide metrics and can provide JSON logs, and it can also react right in the kernel. Here's the kind of views that we can have based on Tetragon data. This shows a pod in a namespace. So we have a crawler pod in the tenants jobs namespace. And based on what Tetragon has observed, we can see all the processes that were executed one after the other with the dates. We can see that the main process is a node JS server that made requests to Twitter and an application with an Elasticsearch label. And then 5 minutes later, there's something weird. There's a shell that was started with an NC to a weird DNS name using notreverse.shell.com, totally not fishy. And then again, 10 minutes later, there was a curl to Elasticsearch, which looks like someone trying to get data from your Elasticsearch and sending it outside of the cluster. So with Hubble, with Cilium, we could see that this pod has access notreverse.shell.com, but actually understanding what happened is where Tetragon shines, and even potentially blocking this attack if you have the rules in place to block this kind of attack. So what I'm suggesting now is we're going to have a little bit of fun with labs, because there's no wrong in having fun learning things, I think. So what we've prepared is we have a map with lots of different labs. It's organized by island. There's the base island here with different personas. There's like the network engineer, there's platform engineers, the security people, and then every island has a different topic. There's observability, there's networking, there's mesh, there's security, and each of them can be explored separately, and you can explore the labs individually. At the end of most of the labs, not each lab, but most of them, you can actually win a badge if you finish the lab. There's a little exam at the end of the labs, and you get a credly badge. If you actually find one of us at a conference, I have stickers that I can give you for those badges, actually. So the way this starts is we have a little quiz. This is a fun little quiz with just a few questions that will tell you if you're more of a network person, security person, or platform person. I expect most of you will identify more with platform engineering, but you never know. And at the end of this quiz, it will redirect you to a lab that is the best for you. So I'll wait a little bit. I can actually open this here. So this is a fun little quiz. It just takes a minute. It also asks for your personal information. And the reason why we ask for personal information is because you get the badges at the end. So if you don't, you're free to actually provide the accurate information or not. If you don't, you won't get the credly badges with the labs. So I'll leave time for everyone to go through this, and then we can start. I'll start one of the labs. Probably I'll start the platform engineer lab to follow along. But again, you can choose whichever you want. There's no right and wrong answer in this quiz, right? It's more fun to find out what you care about. The link is misspelled. How is the link misspelled? Oh, platform. Yeah, I'm missing a T. That's right. Okay, I guess I was a bit tired when I. So the link is, but this is correct actually. So I guess I guess
Yeah, I think your live link is actually misspelled.
yeah, okay, sorry about that. I'll be expelled from the conference for that, I guess. All right, so once you finish the quiz, you will see, do this.
Yeah. So
Wait.
once you go through that quiz, we have another question that came up in Slack from Keith. Do we have any performance comparisons between other networking providers and Cilium in terms of pod startup time, CPU, memory usage, etc.? And the answer for that is yes. So there have been a number of kind of bake-offs that have been done externally to those who contribute to Cilium. We also have some items which are published directly on the Cilium.io blog post as well. Some of those are a wider piece where they look at Cilium itself. Some of those actually look at features of Cilium, such as the XDR features within the layer 4 load balancing capabilities, for example, as well. Again, it's always a little bit hard in terms of being able to give we can produce general information, which kind of works for most people. But then when they start to implement it in their environment, you're always going to find it's a little bit of a snowflake thing in terms of when you run your own bake-offs. Because, for example, if you're focused on network policies, you know, the more network policies that you start to implement inside of your environment can have a knock-on effect. There's a whole page on the Cilium.io docs that talks about performance tuning. So out of the box, for example, Cilium is designed to work for the mass number of platforms and environments that you can install it on, rather than being highly tuned network performance out of the box as well. So there's a number of features that are not enabled by default that could massively improve as well. If you wanted kind of a quick idea of kind of where you could see some of those improvements, one of the labs we have available is on a feature called Big TCP. And essentially it's increasing the packet size of TCP that can be used within a network as well. And some of those network improvements from a very simple Cilium configuration can actually have a massive performance benefit in your environment. However, not every Linux kernel today supports those options, so therefore it can't be enabled by default. You know, as part of the Cilium installation, it will be something you need to plan for, test, and execute yourself.
Yeah. So once you've done the test, you have a lab that is suggested. Maybe I'll go back so you can see it. So there's a lab that is suggested. In my case, I got security, but you can choose another one if you want. So there's platform, there's network, or you can choose from the map. I'll be starting the platform lab because that's probably what most of you are interested in at this point. These are short labs to get you an idea of the different features, and there's recommendation through the lab for other labs if you want to dive deeper. So all of these labs are based on the Instruct platform. You have a VM that is dedicated to your lab session. This one is about platform, and it shows the let's say what we think that platform engineers would be interested in when it comes to Cilium specifically.
Welcome. While your environment
In the context of these labs, you have instructions on this side here. You have several challenges. There's 3 challenges in this lab, and you have access to multiple tabs. Here I have a terminal. I have the Hubble UI that points to the Hubble UI that's running on my VM and on the VM of this lab. And there's a feedback tab in case you need to provide feedback, but feel free as well to provide feedback obviously in the chat or directly here if you need to. So I'll be running this in parallel. You know, feel free to go faster if you want to go faster. Provide feedback, ask questions. You can use the Q&A button still, or the chat, or one of the chats. Don't hesitate at any point to add questions about this. I'll just run through this in case people want to run through it with me. So the first thing I'm doing here is checking the Cilium status. Cilium is deployed in the cluster and the kube system namespace. Sorry, get bought. And you can see here, I've got one Cilium pod per node because it's a daemon set, plus two Cilium operated nodes, two Cilium operated pods that manage the global operations for the cluster. In addition to this, there's actually Hubble relay that has been activated to gather the observability from the different nodes and allow to access them in a centralized way, and the Hubble UI, which consumes data from Hubble relay and shows them in the UI, in the web UI. So this Cilium status, this is a binary that I deployed on my VM, which runs pretty much wherever you run your kubectl command, and it will gather information from all the nodes in the cluster to tell you how your Cilium installation is doing. So you can tell here it uses Cilium 115 open source with so 115.4 with Hubble relay activated, the Hubble UI activated, and you can see the different the status of all the different subsystems of Cilium. Cluster mesh is not activated in this setup here. So we're going to deploy a Star Wars demo. We have an Andor.yaml file, which will deploy multiple deployments. There will be the namespace itself called Andor. There will be the Death Star with service to access the Death Star. And there will be a TIE fighter and an X-Wing. So if I deploy this, if you're familiar with Star Wars, you'll recognize what this is about. If you're not, this is fine. It's just spaceships in space and seeing how they correspond with each other, right? So here we can see that we have the Andor namespace is deployed. We have a Death Star service with a cluster IP and an external IP. It's a typed load balancer. And we have 3 deployments for Death Star, TIE Fighter, and X-Wing. We can actually visualize the traffic by going to the Hubble UI, and you click the Andor namespace. You can see the traffic here. You can see this traffic between TIE Fighter, X-Wing, and Death Star. There's also traffic going out to Disney.com and Swappy.dev. Swappy.dev is the Star Wars API. I didn't make this up. And you can see some traffic is allowed, some traffic is actually dropped because we have network policies in place. So some of the traffic, some of the egress traffic is actually dropped. So if we look here, if you click on the X-Wing, and again, this lab is very basic just to show you most of the features, but you can dive into a specific topic if you want to dive deeper into network policies, for example. There's labs on network policies. So if I click on X-Wing here, it will filter on the X-Wing, and I can tell that the X-Wing is trying to access Disney.com, Swappy.dev, and the Death Star, and all this traffic is dropped. Why? Because we have a network policy in place. It's a Cilium network policy in the Andor namespace. You can see here, there's policies for the Death Star, for DNS, and for TIE Fighter. And because of this, and there's no network policies applying to the X-Wing doesn't have any rights, so its traffic is actually denied. You can actually even see layer 7 information. If you click on the Death Star, you see traffic coming from the TIE Fighter, for example. And you see the TIE Fighter is accessing the Death Star using HTTP on port 80. And you can tell that there's actually a post request being made to /v1/request landing. You can actually click on one of these requests here on the post request, and you could put this bigger, and you can see the details of the flow with the source pod, with the source identity. This is the internal Cilium identity, which allows you to debug what is happening, the labels for the source IP, and so on and so forth. Okay, and again, this recommendations of labs that if you want to dive into layer 7 observability, for example, the golden signal lab is the most interesting one for this. It's not the only one, but it's the one that goes deepest and on this topic. Now, if we switch to the second challenge, this is about providing external access. This is something important when you talk about platform engineering. How do you give access to your pods, to your workloads from the outside? There's different ways of doing this. So let's inspect the different ways and how it has been implemented here. So first, you might have noticed when we looked at the service here, if you do anything to activate the lab, no, not necessarily. Just refresh. Maybe it might be an error on the instruct side. I think I've seen this kind of error sometimes. It's pretty rare, but or maybe you have an ad blocker that is blocking this JavaScript library. So you see here that the Death Star service has an external IP. It uses the load balancer type. If you're familiar with Kubernetes, you know that there's essentially three types of services. There's the type cluster IP, which provides a virtual IP inside the cluster for internal load balancing. And then you have node port, which does the same thing, but it will link a specific port here, in this case, 32.372 on every node. And this port on every node will link to the service, to the cluster IP pretty much, or to the pods behind the cluster IP. And the load balancer type provides a possibility to have an external IP. Now, this load balancer type is a standard specification in Kubernetes, but not a standard implementation. It doesn't work out of the box in Kubernetes. You need a controller that will check services of type load balancer and provide an external IP. It's not automatic. Cilium actually does this out of the box. And the way this is done here, I think I can show you a bit, but there's labs that go more in depth on this, is that we have, in this case, we're using, no, I'll wait a bit, I'll show you it, sorry. So let's see if it works already. Yes, I can actually access this IP address here and access the service. The way this is done here is that it uses LBIPAM. So we have an LBIPAM. I'll show you here. Keep control, get Cilium, load balancer IP pool, and we have one that is called pool here with a rule. I'll just pipe it here for some colors. And you see here that the specification for this Cilium load balancer IP pool is that it provides IP addresses from this CIDR, which is really small. It's just for the demo. You could have a much bigger range. And so this will automatically provide this. So whenever we have a service that is started, Cilium will provide this an IP address for it. So this is the IPAM part of it. Now, how is it announced? In this case, if I'm not wrong, in this case, we're using L2, right, to access it. And this is, again, we have labs that go deeper on this. We have Cilium L2 announcements. This is very practical for home labs typically, but we know people that also use it in production. And here, this Cilium L2 announcement policy, what it will do is that whenever there is a request for this IP address, we're instructing the nodes to reply, to provide an ARP reply for that node, right? So here, this applies to all the nodes that are not control plane. And so there is a node that is not a control plane that will take this leads and will reply to the ARP request for this IP address. And as a result, the traffic will be redirected to the node. So this allows to pretty much take any IP address and assign it to a node in the cluster. As long as you access it on the same layer 2 network, it will route properly. Now, if you don't have a layer 2 routable network, then you'll have to use layer 3 for this. And this will typically make use of LBIPAM plus BGP, which is, for example, detailed in the, or shown in the networking discovery lab, and there's several labs around the usage of BGP in Cilium. So now if we go to Hubble, in the Hubble UI, we can see that we access the Death Star from world. And we can see if we click on world that this was actually successful on port 80. So we can see this here. and world being something outside of the cluster. In this case, it's the IP of the 123 of my VM that I accessed it from the VM itself. Now, this is great, but we're using layer 4 services, right? This is fine, but not extremely fine-grained. Darth Vader is not really happy because he'd like to have HTTPS instead of HTTP. And here we've been using the service with HTTP because this is just layer 4 traffic, right? And my pods don't understand HTTPS. So what we're going to do is typically use an ingress controller, an ingress resource type. Again, in Kubernetes, the ingress resource type is standard. It's a standard API, but there is no standard implementation. You typically need an ingress controller. And an ingress controller may be implemented by the engines controller or traffic or contour. There's lots of different ingress controllers that you typically deploy in addition to your CNI plugin. Well, in Cilium, you don't actually need this because Cilium provides an ingress controller implementation by default. So here what we have is we have actually deployed an ingress. You can see it here. The specification for this ingress called Destar is it uses the Cilium ingress class name, which is built in with Cilium. So it will use the Cilium ingress controller. And it has a rule, an HTTP rule that says that all traffic upcoming on slash or slash anything, right? That's a prefix, needs to be redirected to the Destar service on port 80. It also uses a TLS certificate. The host name is destar.cilium.rocks, and the secret name where the certificate is stored is Cilium rocks. So if we look into the Endor namespace for its secret, we'll see there is a secret called Cilium rocks, which contains the TLS certificate. In this case, this is a self-signed certificate that I have added for the lab. Obviously, in production, you will provide a real certificate. You can typically use solutions like 123. There, I'm losing my words. Sorry. You can typically use Cert Manager. Thank you, Tobias. Talking too much and now my brain is fried. Typically use Cert Manager to generate the secrets for you based on the ingress specification, right? So here we have the ingress that is specified, and what this does with Cilium is that this actually created a service automatically for this. So now if I access the ingress, you see here curl-s resolve. I'm accessing the IP address of the service. It's not actually here. It's in the cube system namespace. If I'm not wrong, yes. The Cilium ingress is in, so it's a shared ingress. It can be configured. You can have one ingress per one service per ingress, or one global service. Here we have a global one called Cilium ingress, which listens on this IP. Again, the IP was provided by the LBI PAM logic in Cilium, and you can actually access it with the domain name destar.cilium.rocks that we provided, and it works because the certificate is valid for this, right? Obviously, I've installed a certificate locally on my machine to make it work, right? Which wouldn't be necessary with typically a certificate provided with Cert Manager plus Let's Encrypt, for example, or any other valid certificate, right? So great. Now it works. Now we have access through HTTPS. We have an HTTPS route using ingress, and this is great. If we go to the Hubble UI, we can actually see now, let's click on Destar. We can actually see, oh, why don't I see this? This is not normal. Let me check. Go back to Endor. Destar. Oh, there. Now you can see ingress. It took a little while to come. Now you can see there's a special identity in Cilium. The ingress controller is known as the ingress identity, right? If I had used an ingress controller such as traffic or Nginx, I would actually see traffic or Nginx by the name of the pod, by the labels on the pod. But here, this is a special identity in Cilium called ingress. Great. Now, the thing is, if you used to ingress, you know there's some limitations. Typically, well, since the Death Star exploded once, we've actually deployed, the Empire has actually deployed a new Death Star. Let's see, get pods. So we have Death Star and we have Death Star 2, which should probably be called Dark Star, I think, right? But never mind. And Darth Vader wants to start having a service that redirects to both Death Star 1 and Death Star 2. But because we're not really sure if it's going to work well, we'd like to have like some kind of canary rollout where we send some part of the traffic to Death Star 2, but still keep some traffic to Death Star 1. So for this, we need to have a weighted service. And this is not possible with ingress out of the box. So instead, what we're going to use is we're going to use Gateway API. Now, if you're not familiar, Gateway API is pretty much Ingress v2 in Kubernetes, right? The reason why Ingress was in beta for so long and all of a sudden became stable is not because people thought, oh, this is exactly what we wanted, let's make it stable. It's exactly the contrary, is that nobody could agree on what Ingress should look like. So they decided to make it stable and switch to something else, which is Gateway API. So Gateway API is the new standard for layer 7 north-south traffic routing in Kubernetes. So what we've done is we've deployed a gateway resource in the Endor namespace. So this gateway resource, you can see what it looks like here. Let's put some color here. We have a specification here. It uses the gateway class name called Cilium, which comes out of the box with Cilium. And we have listeners. And you can tell that this is a little bit more, so this is only part of what the ingress does here. We have some security feature here, which says that the routes are only allowed from the same namespace. So we won't be able to attach this to a route that is in another namespace. It's possible to do it if you specify it here. But this is great, especially from a platform engineering point of view, because as you might know, ingress doesn't have that possibility of secluding traffic per namespace. It's pretty much global, and you could have an application steal traffic from another namespace with ingresses. With Gateway API, this is not possible. We have the host name. This is the part linked to the TLS certificate that we had in the ingress, and we have the port. But you see here that we don't have the logic of which service is being served by this, because this logic doesn't belong to the gateway. The gateway is the administrative part, is the platform part, the platform side of the specification. But now, when developers will want to add their service to the gateway, they have another set of resources. And the resource we're going to use is called HTTP route. So this is a great thing, I think, especially from the platform point of view, is that Gateway API separates the administrative part, which is setting up the gateway, which ports are allowed, which IP addresses, which protocol, which certificate, and so on. This is administrator stuff. This is platform engineering, from actually using the gateway, which is the routing, so the HTTP routes. So if we look at the HTTP route, we have here HTTP route 991, which uses the TLS gateway that we just deployed before. It uses the hostname deathstar.cilium.rocks, which is going to work because the platform engineering team has actually allowed this on the gateway and linked it to a secret that contains a certificate valid for this hostname. And then it has the rule saying, for this prefix, send the traffic to both this Deathstar and Deathstar2 services on port 80, with 99% of the time hitting Deathstar and 1% of the time hitting Deathstar2. So again, this is not possible with the ingress resource type. Let's apply this. This is now configured. We can inspect it. That's what we just did. And now let's make a request. So the IP address is slightly different here because we have a TLS gateway that is dedicated here for this namespace. If we had a global gateway cross namespace, that would be different. So here the gateway is part of the namespace, in this case. Now, if we make a request to it with desktart.cilium.rocks, again, we can access it. And what's going to be interesting will be to look at which hostname we get. Here, I fell on desktart1. This is called desktart. So let's make a little loop, and we're going to make 200 requests to the desktart. I'm making 200 because, you know, if I'm not lucky, I might not see anything on desktart2 if I make 100 requests. So I'm making 200. So let's see, we made 200 requests and stored the responses in code responses.txt. Now, if we grab in there, you can see we actually got three requests to desktart2 and 197 to desktart1. So we're actually indeed getting 2% of the requests roughly to desktart. So 1% of the requests to desktart2 and 99% to desktart1, right? Which is what we wanted. So we could very well adapt this HTTP route to have something more. If we want to roll it out, we can then switch to 50 and so on and so forth. I just need a controller to adapt this. In the Hubble UI, nothing has changed because the gateway API uses the same ingress identity as the ingress controller. This is the same logic. It goes through Envoy. This is Envoy actually doing the layer 7 routing. Now, for the record, we could also have multi-cluster connectivity. We're not doing this in this lab. If you're interested, there is a lab on cluster mesh, which I think is one of the most interesting labs. If you're interested, I'll do a little vote maybe in the chat afterwards to see what we do after this one. In the last challenge here, we'll look at troubleshooting and observability, which is also super important in the context of platform. Understanding what's happening both on the platform side, but also on the application side, without deploying too many tools. All right, there was a little bit of setup for this one. So we want to monitor the resources on the cluster, right? So what we have done is we've deployed a Grafana deployment with Prometheus. So it uses the Prometheus stack. You can see here, we look at all the pods on the cluster. We have the desktart and so on in Endor, and there is a monitoring namespace that was added with pretty much a Prometheus stack. The standard Prometheus stack was Prometheus, Grafana, Alert Manager, and so on. We've deployed some specific dashboards that you can find on grafana.net in the ITV namespace. So we can have a look at this. If you want, there's a little fun thing here. You don't have to do this. So if we look at the network overview here, you can actually see an overview of the network. And this is all provided by Hubble out of the box. The only thing I had to do was to deploy Grafana and get the Prometheus metrics into that dashboard. So what we can see is we have the flow processed by Hubble by type. So we have different types. So there's layer 7 DNS, there's layer 7 HTTP, there's layer 7 of other types. There's traces, policy verdicts, and so on. So these are the different Hubble flows produced by Hubble. The flows produced by verdict. So in green, you would have dropped. If you had some drops, there's forwarded, redirected, traced, and translated. So most of it here is actually forwarded. And here you have the top 10 sources and top 10 destinations in the cluster, right? And you have the missing TCP syntax, missing ICMP echo replies, and network policy drops by source. So this can allow you to debug things pretty well. Here, this is in the default, sorry. Here we have the cluster if you have multiple clusters, and you have the namespaces. So here we see in the Endor namespace, but you could filter by namespace here for the source namespace and for the destination namespace. So that's the first part. There is actually a problem in our cluster, but it's DNS actually. And we can see by looking at the DNS graph here, the DNS queries have gone down, and there's a missing DNS response graph here that shows that we have DNS responses that are not being returned. So Cilium is seeing DNS requests without an answer. And we can even see which DNS queries are made mainly. It's the Destar, Sevis, and the Andor namespace, and Disney.com and Swappy.dev. This is number of requests per second. All right. So let's try to figure out what is happening here. We can try to use Hubble in the CLI for this. So if we do Hubble observe, this shows us the Hubble flows. And then we can filter from core DNS to world. Trying to understand, we might have tested other things before, but trying to understand how core DNS is talking to the world. And we see here that there's requests being made to 1234 on port 53. And now if you know 1234 is not a DNS server, there's clearly a misconfiguration here. Something was broken. It was actually broken during the setup of this challenge. So what we're going to do here is fix it by editing the configuration for core DNS. And here the forward should be sent to something else. Here we're going to set it to 8888. This is what's expected to pass. All right, this is not great, but at least 8888. Everybody knows this DNS server, right? And once this is done, we can redeploy core DNS by doing a rollout restart deploy core DNS. Now, if we look again at the traffic, we can start seeing requests to 8888, and eventually they will only be 8888 in the flows. So it looks like this is going better. If we go back to the metrics here, we'll see that that this is being fixed. Where do we see this again? Boom. I don't remember why I see the DNS part here. No, this is not here. But in DNS here, I will actually see the missing DNS responses going down. Again, there's some labs that go deeper on this. The Golden Signals lab uses these dashboards to show how you can monitor your applications using this out-of-the-box metrics. Once this is fixed, we can finish here. And if you've done everything, you will get the badge for this lab. Again, this lab is super simple. It doesn't go very much in depth. So what I'm suggesting, because it's been an hour and a half, if you want, I'm happy to do a second lab in this workshop. There's lots of choice. What we find is that a lot of people interested in platform engineering actually like going towards Gateway API and diving more into Gateway API. So there's a Gateway API lab, there's a Gateway API Advanced lab, there's even how to configure and program Envoy, some examples of advanced layer 7 routing. There's other things, if you want, we could dive into cluster mesh, into network policy, encryption, and so on. So if you have suggestions on what you'd like to see next, unless you want to do it on your own, this is fine as well if you want to do the labs entirely on your own. Don't hesitate to comment in the chat if there's a lab you would like me to comment on in the next hour. Meanwhile, there's a question in the Slack channel about Tetragon. Does Tetragon primarily operate on layer 7? So Tetragon does not do networking. It doesn't do networking routing or networking security, but it can observe connectivity. It can observe the creation of network sockets. It can observe layer 7 traffic as well. So Tetragon in this context is essentially used to observe how a process behaves, what kind of connections a process can make, and potentially parse the traffic, including layer 7 traffic. Does that answer your question? So what's interesting with Tetragon with regards to layer 7 is that Tetragon actually parses layer 7 with eBPF, something that Cilium does not do yet. It mainly relies on Envoy at this point, but it shows that it's actually possible to parse HTTP traffic using eBPF, and that it will be coming as well to Cilium at some point. How's it going with everyone? I don't see anyone typing in the chat. If you want to say something, do you want to do something else? Otherwise, I can start the Gateway API lab. Cool. Let me check very quickly. Check the sandboxes here. Yeah. All right, let's go with Gateway API. So like I said, Gateway API is essentially the replacement for a Kubernetes ingress. This is Kubernetes ingress V2, if you will. We have 2 labs on Gateway API. This is the first one. You can feel free to take the advanced Gateway API after that, which goes more in depth into other use cases with Gateway API. There's a lot of things that can be done with Gateway API because it's much more featureful than ingress. So let's zoom a little bit here. All right. So what are the conditions for Gateway API? Cilium must be configured with kube-proxy replacement. So as I mentioned before, Cilium has the possibility of replacing kube-proxy in a Kubernetes cluster, right? Kube-proxy is this component. I think in this case, we actually don't even have a kube-proxy in the cluster. You see here, kube-proxy was entirely removed from the cluster. The way we configured this cluster, if I look at, so this is a kind cluster, right? To make it simple, this is not a prediction cluster, but here we have disable default CNI and and I'm sure I disable kube-proxy. Oh, here it is, cluster.yaml. There it is. This is what I used. So I disable the default CNI, so there's no default CNI when I install Cilium, and kube-proxy mode is none. So I created a cluster with 1 control plane, 2 workers, no CNI, and no kube-proxy. What this means is also when I installed Cilium, we can check it. Actually, I use Cilium install, but it uses a Helm chart. If I look here in the kube system namespace list, you see there's the Cilium chart, and I can have a look at the values. You see, these are the values that were passed. In this case, I use Cilium installed with Cilium install, so the Cilium CLI with these values. Oh, there's an extra backslash. I should remove this. So it's version 1.15.4. We installed to the kube system namespace, set kube-proxy replacement to true, and gateway API.enable.true. We also added a few more things here. Because we set up kube-proxy replacement to true, we need to tell Cilium where is the kube API server accessible. This is important because since we remove kube-proxy, there is no longer a default Kubernetes service available in the cluster. It doesn't work because there's no kube-proxy, right? So we need to tell Cilium how to access the Kubernetes API so that it can implement it. So here we're accessing using the public IP address from this cluster. So this is how you access it with kind. This is pretty much what I have in my kube control configuration. We have gateway API enabled. We have the devices that need to be controlled by Cilium, only ETH0 in this case. The iPine mode is Kubernetes by default on kind. And we're going to use L2 announcements, just like in the previous lab, so that we can access the services from the VM using ARP. We're using tunneling for the routing mode. This is the default using VXLAN, so it's encapsulated. We're not using direct traffic, direct routing. So again, we do Cilium status -- wait. Everything is running fine. We have Cilium running. This is actually Hubble is disabled in this case. We're not using Hubble yet, at least. I don't remember if you're using this one. We can check that everything is configured properly. Cilium config view actually gives you the configuration for Cilium, the whole configuration. There's another way of seeing it. If you look in Cube System, you can look at the config map called Cilium config, and you will see pretty much the same values. So, like I said, Gateway API is really great from a platform point of view because it really separates the administrative part from the usage part. So in Gateway API, there's a concept called Gateway class. And you can think of it, I mean, when I started with Gateway API, I thought of it a little bit like storage classes, right? You know how in storage management in Kubernetes, there is a separation of concerns between the platform side and the usage side, with storage classes taking care of creating the PVs and users actually using the PVCs to make claims on the physical volumes and use them. This is pretty much the same here, where we have the gateway class that will allow administrators of the platform to implement the gateways and then let users declare the routes they want to add to these gateways, which I think is really great. So here we have one gateway class that was deployed by Cilium out of the box, and it's called simply Cilium. So this gateway class simply exists, and it has a controller name, which allows Cilium to control the resources managed by that gateway class. Again, think of it a little bit like storage classes in the context of storage in Kubernetes. So this is what it looks like. The infrastructure provider provides the gateway class. In this case, Cilium provides the gateway class and implements it. Then the cluster operator, so typically platform engineers, will implement the gateways and decide on which ports are used, which TLS certificates, and so on and so forth. Is it multi namespace, and so on and so forth. So this is administrative tasks. And then the developers will be able to add routes and attach them to the gateways following the rules, the security rules that the operators have put in place. So let's click on check and go forward once this is in place. Don't hesitate if you have any questions to ask them, interrupt. We're going to deploy a very, very common application called Bookinfo. It's used by a lot of demos all over the place. This is not Star Wars. I might have to change this at some point in the future. And we need a load balancer. So this is why I've actually activated layer 2 announcements in the Cilium installation so that we can load balance from the VM using ARP to announce the IP addresses. Notice that I didn't have to activate the LBIPAM feature because the LBIPAM feature is actually activated out of the box. It just turns on as soon as you start deploying IP pools for the services. So we're going to apply this Bookinfo manifest, which deploys multiple deployments and services. This is typically an application provided by the Istio project, if I'm not wrong. Yeah, from the Istio project, yes. So if we look at the pods, it takes a little while for everything to run. Let's wait a little bit. It's almost running. You can just run this. Yeah, now all my pods are running. Okay, all good. I can look at the services as well. I have one service for each pod. I have details, product page, ratings, and reviews. And this points to the different deployments. Okay, so far, these are just cluster IP services for internal communication. Now we can deploy the gateway. So let's have a look at this gateway first. It's called basic HTTP. So there's the gateway component. We put everything together, but again, what makes more sense from a platform point of view is that the gateway is managed by platform engineers, and this will be managed by the developers. So the gateway is the platform engineering side, and this says, I want to use the Cilium gateway class name. So this is the implementation. My gateway is going to be called my gateway, very creative. It will listen on port 80, protocol HTTP, and it will allow routes from the same namespace. So this gateway is specific to this namespace, which is the default namespace. And then I'm going to attach an HTTP route to this gateway. So namespace default, my gateway. And then this route has multiple rules. If the URL starts with /details, it will redirect to the details service on port 9080. If it starts with slash and matches headers with name magic and value foo, then and name a great value example. That's the query param, sorry. So with both of these, so the header magic value foo and the query parameter great with value example, then it will redirect to product page. So you can see here the kind of fine-grained traffic management that you can have with Gateway API that was not possible with Ingress, at least not out of the box. Quite a few Ingress controllers provided some of these functionalities using annotations, but this is not very clean. So let's apply this. We created both the gateway and the route. Again, gateway is responsibility of the platform engineer, and this is using it. Yeah, so there's two roles like we saw, the details role and the product page role. And now we can actually test this. I already commented on this. So if we look at the services, there's a gateway that was created. By default, this gateway is created as a load balancer type. And we actually have in place, I didn't show you, but we have a Cilium load balancer IP pool in place, like in the previous lab. Let's do spec. And you can see that it gives IPs from this range again. So very, very similar to what we had, if not identical before. So this gives me an IP address, a public IP address, that I will then be able to access because I've activated ARP announcements on Cilium. Again, in production, you can use LBIPAM, but you will need to use probably BGP announcements to have layer 3 propagation of this IP address. If we look at the gateway, we have the IP address to access it. So let's store this in a variable called gateway. And now we're going to make the requests. So if we make a request to the gateway IP address on /details/1, we do get the first element for the details, right? In the details service. This works. So the /details was redirected to the details pod, to the details service. Okay, great. And now if we match by header, we can do this. Let's have a look at the URL. We passed the header magic foo and the query param grade equal example. What if I don't do this? Then I get a 404 because my routing logic here is based on both the header and the query parameter being in place. So you see that you can have very fine-grained routing with these things. All good. Let's move forward. So now we want to add HTTPS. We want to add a TLS certificate to our service. So what we're going to do again, we could use Let's Encrypt in production. In the context of labs, trust me, I've tried. This is a mess because I don't have a DNS that I can assign to every session. So it's a little bit complicated. So we've chosen to use self-signed certificate. We're just going to create a certificate using mkset, which is much easier than using OpenSSL. So this created certificates here, keys and certificates. We have a key, we have a certificate. And then this certificate is self-signed. So if I use it, I'm not going to be trusting it by default, so I'll need to install it. And it is valid for star.cilium.rocks. We're going to add this certificate to the cluster by creating a secret of type TLS. This is what Cert Manager does under the hood, by the way, when you use it. So kubectl creates secret of type TLS. It's called demo cert. The key is this file and the cert is this file. So now we have get secret demo cert, and we have it here in base64, obviously, because this is a Kubernetes secret. Now we can deploy the gateway. We need a new gateway, and this gateway will be an HTTPS gateway. So we have the gateway itself, responsibility of the platform engineering team. And we're going to have two listeners here for two different host names. One, and both listening on port 443, one that will listen on bookinfo.cilium.rocks, the other on hipstershop.cilium.rocks, using the same secret because the secret contains a TLS certificate valid for star.cilium.rocks. And then we'll have two HTTP routes, one for each application, one for bookinfo, one for hipstershop. Bookinfo redirects to /details, to the details service, and hipstershop will redirect / to product page. So here, the traffic will be routed based on SNI. It will be routed based on the domain name that is requested in the TLS request. So let's apply this. There we go. We've created one gateway. So we have a new gateway called TLS gateway. This has created a new service called TLS gateway, Cilium gateway, TLS gateway, created by Cilium. It automatically got an external IP with the LBIPAM system that I've configured in Cilium. And so we can get the IP address for this. Let's store it as the gateway IP variable, and then we can start making requests. First, we're going to install the certificates on our machine. This puts it into etc SSL so that when we make requests with curl, it will be valid. If I don't do this, then my request will not be valid. The TLS won't be valid. So I can make a request to bookinfo. And when I make a request to bookinfo, you can tell here that it gets directed to details because it matches both /details and the bookinfo domain name. All right. Okay. Next. Don't hesitate, scream in the chat if you have anything you want to stop me for. Sometimes you have services that actually do TLS on their own, and you need to match on SNI for traffic routing, but let the application manage TLS. In this case, we're not going to do TLS termination. We're going to use a TLS route that will send the traffic. So it will pass through the TLS traffic to the pods. So let's configure this. We're going to use Nginx as the pod, as the server. And this is the configuration here. So Nginx is going to listen in SSL using port 443. It will actually use nginx.cilium.rocks as the server name. So we're going to create the configuration, the config map based on this file. Great. And next, we have a TLS service. So this TLS service will use Nginx. It will mount the configuration from the config map we just created. We also have an index.html that has been created as a config map in this lab. You can actually look at it, get config map index. There you go. This is a simple HTML page. And what else? Yeah, so that's the deployment for Nginx. It also has access to a secret, which is a demo cert for the certificates that we created earlier. So it has access to the certificate so it can serve HTTPS with the start.cilium.rocks certificate. And then we have a service that will serve this Nginx traffic on port 443. Okay, so let's apply this TLS service. So we created the deployment. Here's the deployment, my Nginx, and the service called also my Nginx. It's a cluster IP type of service. We could obviously just create, expose it using an external IP as a service of type load balancer. That would work. If we want to avoid this kind of thing, typically because this would mean that developers would need to have the right to do this. Instead, we're gonna think in terms of separating the concerns and considering that developers are not given the right to do this. So they're not given the possibility of using labels that will assign an IP using LBI-BAM. And again, you can configure this with webhooks in Kubernetes to prevent developers from using the right labels that will give them this, so preventing them from creating load balancer type services. So here, instead, we're going to use the gateway that has been configured by the platform team. If we look at this, we have the service, we have the deployment. Now we can deploy the gateway. So the gateway is, again, twofold. There's the gateway on one side and the route on the other side. The gateway is a TLS gateway. And it's configured as a pass-through gateway. So it will use TLS. It will use TLS for SNI. So it will actually look at the domain name that is requested for the TLS communication. Based on this, it will allow to route the traffic to the my Nginx service, but it will not terminate TLS. Instead, it will pass the whole TLS traffic to the server, and the server will terminate TLS communication. So let's apply this. And now we can see the TLS gateway and its address. So we can make requests to the address. Right, we can see the condition here. That can always be interesting. You can look at the status. So we see the TLS route was accepted, service reference is valid. So this is ready to go. You can use this to debug the status of your gateways as a platform team. So here we're making the request, and you can see that we're indeed getting to nginx.cilium.rocks 443, and we're getting the HTML that was set in the config map. So all is well. And the traffic, the TLS connection, the TLS handshake and connection was actually managed by Nginx. So again, Nginx is probably not the best example for this, because you could very well use HTTP for the service and let Gateway API do the termination. But there's other services that would require something like this, maybe PostgreSQL, for example, or other databases using TLS, where you would want them to do the TLS termination themselves. Something that we've seen a little bit in the previous lab, and we're going to dive a little bit more into this, is traffic splitting, the possibility of splitting traffic left and right between different services. So let's have a look at what we have here. We have two services, Echo 1 and Echo 2, so two deployments and two services. We can apply it and check that the applications are properly deployed. We have this, Echo 1, Echo 2, the pods are ready. And we have two services, Echo 1 and Echo 2, listening respectively on port 8080 and 8090. Now we're going to load balance traffic equally. So we're going to put weights of 50 and 50. So half of the traffic will go to each of the backends. All right, so if we do a request to the gateway here, we get sometimes Echo 1, sometimes Echo 2. Still Echo 1, Echo 2 now, right? So if we make a lot of requests, let's say 500 requests here. And we have a look at the responses. We see we get roughly half-half between echo 1 and echo 2. Now, if we wanted to have like a 99 to 1, we can simply edit the route. So here we're editing directly in the API server, right? Downloading the manifest to temporary file, editing it and sending it back. Obviously, in production, you want to do something a little bit cleaner, maybe some kind of using Argo CD or Flux or whatever else, some Git logic, right? GitOps logic. So I'm going to put 91 to 1, 99 to 1. And now that this is done, I can run my requests again. And now I get roughly one for 100, right? It's roughly 5 for 500. Okay. All good. Again, this could be, you could add things in there. So all the routing based on headers, based on parameters, based on path, TLS, and so on, all this can be mixed, obviously, for complex situations. So let's do a final quiz on this. Again, this does not cover everything with Gateway API. We have a Gateway API Advanced Lab, which goes even deeper on Gateway API features. And every feature of Cilium pretty much provides new Gateway API related configuration. What I'm really excited for personally is the Gamma project, which promises to use Gateway API constructs for in-cluster routing, which means layer 7 routing inside the cluster using Gateway API resources. This is not there yet. There's some projects that are starting to add this, and this is clearly on the roadmap for Cilium as well. So what is true here? Ingress API is the long-term replacement for Gateway API. No, it's the contrary, right? Gateway API is the long-term replacement. One of the benefits of Gateway APIs is that it is role-oriented. Yes, and especially for platform engineers, it is role-oriented. There are some CRDs that are made for platform engineers and some for consumers of the cluster. This is really great as far as security is concerned and separation of concerns. The gateway and HTTP route configuration is all defined in a single API resource. No, there's several API resources. This goes with this benefit of being role-oriented. Cilium Gateway API requires kubeproxy replacement. That is true. So we need Cilium to manage kubeproxy, to replace kubeproxy in order to do this. And Cilium Gateway API does not support L7 HTTP routing. Well, on the contrary, it does. So the last part is the exam. So the advanced labs, so like this one, have a final exam challenge. And you need to earn that badge because that's a silver badge. No, it's not a discovery badge. So I'll give you a few minutes to start looking into this. Maybe I'll do the description. It's not a very complex exam in this one. So we will reuse the services called Echo 1 and Echo 2 that we created earlier. Here, Echo 1 and Echo 2, they're right here. And in order to pass the exam, we need this. Both services should be accessible via Gateway API. HTTP traffic based on the prefix path /exam should reach the services, with traffic splitting 75 to 25 between Echo 1 and Echo 2. You can use the editor. You see here in the editor, there is an exam gateway.yaml with some XXX that need to be replaced and a route with also some XXX that need to be replaced. All you need to do is find the right values to put here and apply the manifests. You can actually check your work with curl at the end. And when you're done, when you've deployed everything and you think this is all good, you can click check. And if it passes, you'll get the badge. I'll wait a little bit and maybe like in 5 minutes, I'll start doing it. Nice, good to know that you enjoyed the networking lab, Jürgen. So again, all these labs are accessible anytime. You might not be able to access with the code that you got this time. It's only valid for 5 days. But if you go to isovalent.com/labs, all these labs are free. You can access them anytime you want, or you can access the map as well, like we saw earlier. And as you progress through the labs, once your code expires, you might need to go through a form again, but once you've put your email address, it will recover your progress. You'll see which labs you finished, and you can keep exploring the different labs. Right, so the values are not very hard to find. If we look at the services, Echo 1 and Echo 2, you see Echo 1 is listing on 8080 and Echo 2 on 8090. So we'll just need to put 8080 for Echo 1 with 75% of the traffic. Echo 2 gets 8090, 25% of the traffic. We want this to be on /exam. And the name of the gateway should be, will be here. It's called exam gateway. Exam gateway. And then the exam gateway itself, the class name is Cilium. We're using the built-in Cilium gateway, and that's pretty much it. So if we apply this, exam gateway, created the gateway here. There we go. Exam gateway is created. It's got an address that was assigned to it. And then the route, HTTP routes, and we have the route for the exam that was created. There's no host name, so it's not a TLS gateway. So this should be fine. Now, if we assign, if we do something like this, there, let's manually put the IP address here for the exam gateway, which is this one. We get Echo 1, sometimes Echo 2, 25% of the time. This looks correct. All right. So this should be fine. I'm done. Good luck. If you're still doing it, you see it's not extremely hard. You just need to find the right values. So to conclude, there's an eBPF YouTube podcast. If you search for Echo eBPF or Echo Cilium on YouTube, it's also on LinkedIn. It's also on lots of different platforms. Every week, there's hundreds of episodes that are available that have been recorded on tons of topics. So you can feel free to look at this or even participate, attend one of the recordings on Friday afternoons. Every other week it's in US time, every other week it's in EU time. Then there's the Echo News, which is a newsletter that is published every 2 weeks by my colleague Bill Mulligan, and summarizes lots of news on tooling, blog posts, videos, events, and so on around eBPF and Cilium. And finally, there is an eBPF and Cilium Slack that you can join to ask questions. Lots of topic there, and obviously you can continue with the labs. You're most welcome to continue. If you have any issues, any comment, don't hesitate to leave them at the end of the labs or to reach out to us. We're always happy to see what people think. If they enjoy the labs, if they have problems with labs, we're happy to reach out as well. So I hope this was enjoyable for you. I hope it was useful. I wish you a great day. Have fun for the continuation of this conference. And yeah, see you around. You know where to find me if you need to. Take care.